right? I thought there'd be data. Is anyone out there?
Hello and welcome back. Okay, so we are doing UMPs. We're kind of finishing up UMPs. We only have a UMP for simple versus simple. And then at the end of last time, I was defining a UMP for simple versus composite by saying that it's UMP for every simple versus simple that you can pull out of those set of hypotheses. And yeah, and so I want to say a little bit more today about what happens when the null hypothesis gets composite, but I do want to spend more time on GLERTs. I love saying GLERT. It stands for GLRT, Generalized Likelihood Ratio Test, because we have places that we've already seen where UMPs don't exist, which mostly come from the like the difference between an equals and a not equals. But I also did promise you that things would get a lot weirder than equals and not equals and less than, and that's really where the GLERT shines, because we really haven't done any of that yet. Okay, so two more UMP examples. So this one is just for simplicity, so we don't have to force everything to be a chi-squared. I'm going to look at a sample of size 1. So consider a random sample of size 1, so it's nice and analytically manageable from the distribution with PDF. So f of x and theta is going to be 1 minus theta squared times x minus 1/2, and that is going to be for all x between 0 and 1. And the parameter space here is thetas between -1 and 1. And so let us try to find the uniformly most powerful test of size alpha of the null hypothesis that theta equals 0 versus the alternate hypothesis that theta is not 0. So this is mostly an example of showing you that the not equals does not have to mean it doesn't exist. Okay, so we're going to first consider, so step 1 is to first break this down to a simple versus simple. So let's consider testing versus the alternative that theta is some theta 1, where theta 1 is just a fixed value that's not equal to 0. So this guy is fixed and not equal to 0. And so I'm going to apply Neyman Pearson. Okay, so let's form the likelihood ratio. It's usually not referred to as a likelihood ratio for the UMP test, but it is a ratio of likelihoods. And so I want to look at the thing we're calling lambda. I'm going to plug in 0 and I'm going to plug in theta 1, which looks a little strange. So if it helps you, then just call 0 theta naught. But this is f of, so there's just a single x. I'm not looking at a joint PDF. At 0 over f of x at theta 1. And so when theta is 0, going back up here, this whole second part zeroes out, and it's really just a uniform PDF. So this is just the indicator from 0 to 1 of x over all of that other stuff. 1 minus theta 1 squared, x minus 1/2. And
quick question.
Yeah.
Does the fact that it's theta squared, because like you can't tell if from the PDF if theta is negative or positive because the square deletes that information. I was wondering if that poses a problem.
Yeah, it won't for this test because we're just trying to say theta is 0 or not 0. So theta squared being greater than 0 is just going to be evidence that theta is not 0. So I'm going to cancel and write this as 1 over this stuff. I'm serious, draw me a hand turkey. I'll take it. This is less than or equal to some k. We're going to set it less than or equal to some k. And then as usual, we want to kind of isolate the x stuff. So if I flip both sides over, I get 1 minus theta 1 squared, x minus 1/2 greater than or equal to some k1 or k2. And k1 happens to be 1 over k because I flip both sides. And again, moving on down to the x, this is greater than or equal to some k2, dividing by this. So no matter where our theta 1 is, because it's just non-zero, so it could be positive or negative, but it doesn't matter because of the squared here. This is always negative, no matter what side of 0 we chose our theta 1. So if you divide, you will flip again and get some k3 and move the 1/2 over and you'll get some k4. And so you'll see that this works for any, well, I don't know why I'm circling that, but the form of the test is the same for any theta 1 that's not 0. And so we're pretty much done because the form, and watch for that on upcoming assignments, and the final, which by the way is just another midterm. It's not cumulative. It's supposed to be 50 minutes. And I think it's even less. I'm pretty sure I put it on the syllabus as 20%, like I did homework at 30%, first 2 midterms at 25%, and the final at 20%. So it's even less because it's a stressful time. Why not? Okay, so the form of, but watch out for the form of the test. I will write this bold and underlined, and this just means to stop with this statement, which is reject the null hypothesis in favor of the alternative if our single x in the sample, so if it helps, call it x1, but I'm just calling it x. Our single x is less than or equal to k4, where k4 is chosen to give a size alpha test. That's the form of the test. And so if you're asked for the form, you are done. Okay, so this is nice and simple, so we can actually find it. So let's find k4. And this is where alpha comes in. So alpha is the probability of the type 1 error. That's the probability you reject the null hypothesis when you shouldn't, because it's true. This is nice and simple. So this is the probability we reject the null hypothesis when the parameter, like when theta is 0. And so when theta is 0, well, let me write this out one more line here. This is the probability that x is less than or equal to k4 when theta is 0. And so when theta is 0, that tells us that the x is uniformly distributed on 0 to 1. Sorry about the scroll, but let me just go back and show you the original PDF. So from here, if you plug in theta equals 0, you just get 1 times that indicator. You get a uniform PDF. And so, great. This is just a uniform 0, 1, which has a PDF of height 1. And if we want to be below some K4 with some probability alpha, then that means that K4 has to be alpha so that the total area of this rectangle will be alpha. So the best or most powerful test of size alpha of the null hypothesis that theta is 0 versus the simple alternate hypothesis theta is theta 1 for some fixed theta 1 not equal to 0, mumble mumble. Okay, so is to reject null hypothesis in favor of the alternative if x is less than or equal to alpha. And because this test, I never started with an x1, but it doesn't look like a sample. Again, if you have a sample of size 1, this is like an x1 less than or equal to alpha, depending on whether you decided to just call it x or call it x1. But the point is to make it uniformly most powerful. First of all, for simple versus simple the uniformly most powerful test is just the best or most powerful test, because the definition is that it is best or most powerful for all of the thetas in the alternate hypothesis. So if there's only one there, then our best or most powerful test is technically uniformly most powerful. But if we want to find the test that is uniformly most powerful for the equal zero versus not equal zero, well, we just conclude that from here. We say this test is UMP for the null hypothesis that theta is zero versus the alternate hypothesis that theta is not zero, because it does not depend on the particular theta 1 we chose. And there's two things to look at when drawing that conclusion, but let me just finish writing that. It does not depend on the particular theta 1 chosen to perform the simple versus simple test above. And so not depending on that, you have to look for dependence in two ways. So one way is that the actual test here does not depend on it. You know, you say, I'm going to reject if my x1 is less than or equal to alpha, not if it's less than or equal to alpha over theta 1, like the test looks free of theta 1. But somewhere in the making of the test, we may have or may have not flipped an inequality depending on where theta 1 was chosen. And it didn't matter in this case because it was this circled guy, it was squared. So, wow, there's a real lag. Like I stopped scrolling a long time ago and I wrote that a long time ago. Right, so this negative theta 1 squared is always negative, regardless of whether theta 1 is positive or negative. So again, two things to look at to say that this test is theta 1 free. One is that you don't actually see a theta 1 there, and the other is to make sure the theta 1 you chose does not affect like whether you're going to have a less than or greater than. So we have a UMP. So if you have let's say we have a composite null hypothesis where we want a UMP test. So this is our first example of something like this. So suppose I have like an x1 through xn, IID, normal, like a 0 sigma squared, or a fixed mu and sigma squared. And suppose I want to find the UMP test of size alpha of the null hypothesis that sigma squared is less than or equal to a constant. So to use our notation that we've been using, like when we have a mu, we usually say less than or equal to a mu naught. So I'm going to say sigma naught, but also squared, but it's still just a constant. But I think it's inconsistent to write sigma squared, to write just sigma naught, which would be fine because it's still just a constant. But it sort of looks like a standard deviation. So versus the alternative that sigma squared is greater than sigma naught squared. So the sigma naught squared is just a given constant. Okay, if you go through, I'm gonna write this as well. I have great plans for this break. If you go through the proof we did last time of Neyman Pearson, with the whole like the probability that X is in C star when the null hypothesis is true is less than or equal to the K, the whole proof we went through last time, which is in the notes, but I'm going to type up again because I want to show it to you in this sort of situation. You'll see that the proof as it is still holds if, so this was for a simple versus simple, and you'll see that it still holds if your null hypothesis is composite, but the maximization that you use when finding your cutoff, your K or your K5 or whatever you're calling it based on alpha, as long as your maximization occurs at the endpoint of the parameter space. So if you are testing theta less than or equal to theta naught, then when you're finding the alpha, you're going to have to do a max over all theta less than or equal to theta naught. And the entire proof we did last time holds up just fine if this maximum occurs at that boundary point. So what I'm claiming is if we were to write out this proof, which I am going to write up for you, we could treat this problem just like the last problem. We could just make this a simple one and kind of consider the Neyman-Pearson ratio, but plugging sigma naught squared in. Then that proof holds up fine. It is not clear what happens with that proof if this maximum does not happen at the endpoint. So I have an exploratory problem in the homework coming out today that, guess what, I actually solved before assigning. So my claim is that you can still use Neyman-Pearson and that you should first just make this simple and really think of this as simple. And you have nothing that needs to be changed as long as the maximum that defines alpha occurs here. And then we are going to explore what needs to change if for some weird reason, because this has never happened yet, the maximum defining alpha does not actually occur at that endpoint. So let's just do one more example and move on to GLERTS, and let's just make it easy. So let's do this example. Normal, 0, sigma squared. And for right now, I'm going to make it nice and simple versus something, I don't know, an inequality. So as in the previous example, if you want to find the UMP test of size alpha, you would start by making the alternate hypothesis simple, and then you would go through the test and you would say, this doesn't depend on the particular simple thing I drew, that I set for my alternate hypothesis. And yeah, I don't know if you want to see this. You want to see this? So let me start it and then say, do you want to see this? Step 1 is to fix a sigma 1 squared that is greater than sigma naught squared, and consider testing sigma squared equal to sigma naught squared versus sigma squared equal to sigma 1 squared. I don't know, I'd love to do it, but you might be just sick of the same thing over and over again, because what I'm going to do is I'm going to form that lambda ratio. I'm going to take the joint PDF with sigma naught in it over the joint PDF with sigma 1 in it. I'm going to set it less than or equal to k, and I'm going to solve down for the x's. And so if you do that, I know I'll do it, but I'll skip a whole bunch of steps. So if you write down this ratio of PDFs and you put in sigma naught squared and sigma 1 squared, and note that the mean is 0 in this case, if you set this less than or equal to k, you will then solve down for the x's, and you will isolate the sum of the x's squared, and it will end up flipping. So this will be greater than or equal to some k12. I don't know how many steps it's going to take you to get there, but some other constant. I'll just call it k1.
Oh, it doesn't also involve the sum of the x's? That's
Yeah, maybe
surprising.
let's do it. I wanted an excuse to do it, and because it's not so obvious, that's a great excuse.
I guess I was expecting like the sample standard deviation to show up in the test, but
yeah, well, the reason it doesn't is because the joint PDF does not have like the minus, the sample mean is 0, so the
oh, okay, that makes
yeah,
sense.
this is going to be minus n over 2, and then e, the minus 1 over 2 sigma squared, sum of the x's. So then when you put in a sigma naught squared and sigma 1 squared and take the ratio and you divide all this stuff to the other side, at some point you will have, I don't know why I just didn't write it out because I'm writing out all the steps and yet it's so confusing because I didn't do it in an orderly way. But if you set the ratio less than or equal to k, then you will come down to a minus 1/2 sigma naught squared sum of the xi squareds plus 1/2 sigma 1 squared sum of the xi squareds less than or equal to some k, k1, k2, k3. And yeah, so this is not equal. This is minus 1/2 1/sigma naught squared minus 1/sigma 1 squared, sum of the x's less than or equal to k1. And now it becomes important that we said that sigma 1 squared is larger. So that makes this fraction smaller, not the denominator, but the whole fraction. And it makes the thing inside the parentheses greater than 0. And so this whole thing with the negative out front is less than 0. And so that is since sigma 1 squared is larger than sigma naught squared. And so when we divide, we end up with the sum of the xi squareds greater than or equal to some k2. That was almost, yeah.
So to make sure I kind of see how this generalizes, if mu were not 0, then in our test somewhere, probably in this k1, we would wind up having the parameter mu. And if we
Yeah.
didn't know mu, then we'd have to use those tricks we did in that one homework assignment to involve x bar instead.
Yeah, and we really can't do that with our UMP test because the Neyman Pearson stuff starts with a simple versus simple, and it's no longer a simple hypothesis. This is exactly what GLERTs are for, the next type of test. But if you're testing,
So if we also assume that they have the same mean, but we just don't know what it is, do you expect that they would still cancel, or would we have to involve x bar?
we would have to involve x bar. Yeah, they wouldn't cancel because it's still a composite set. The two hypotheses would still be composite because given that you know that this is true or this is true, you still don't know exactly what the distribution is, even if you're assuming only one mu. Well, of course there's only one mu. There's a mu here though, and if it's unknown, then like none of this makes sense. It's just not simple anymore because the distribution is not completely determined by this. But there is a test. This is what the GLERTs are for, and yeah, the test is also going to involve x bar. Okay, so I guess I wrote step 1, so I'll write step 2, which is to find the k2 or k5, or maybe you reuse the name k. So the alpha is the probability of the type 1 error because we're in the simple null hypothesis case. This is the probability we reject the null hypothesis when the parameter is sigma naught squared. This is the probability that the sum of the capital Xi, I don't know why I'm writing that as a fraction. The sum of the capital Xi squared is greater than or equal to K2, sigma naught squared. Okay, so the X's were normal, 0, sigma squared. And so there's a couple of ways we can go about this here. We can use the fact that when the true parameter is sigma naught squared, that's saying that the x1 through xn are IID normal 0 sigma naught squared. And so that implies that each xi divided by sigma naught is normal 0, 1. And that implies that if you square this whole thing, you have a chi-squared 1. We saw early on in the course that a normal 0, 1 squared is a chi-squared with 1 degree of freedom. And we saw that if you add up independent chi-squareds, then you get another chi-squared and you get to add up the degrees of freedom. So under the assumption that this is the parameter, then this has a distribution that it, nice purple highlighter on there. This has a distribution that is chi-squared with n degrees of freedom. So I guess we can make our test based on a chi-squared critical value.
We
Yeah.
need to divide
Oh,
by.
no, yeah, divide, right. For using this conclusion, I need this, thank you, I need the sigma naught squared over there. So I'm going to do that, and sorry about that. So I'm going to divide both sides by sigma naught squared. Okay, and then this guy here can be written as the sum of xi over sigma naught all squared, which now is a sum of chi-squared ones. And so we can write this as like the probability that some w is greater than or equal to k2 over sigma naught squared. And I'm kind of done with this additional information. Could you call this thing a K3? You could, but it depends on what you want to report. And the test, which I never actually wrote down back here, I want to make the test to reject the null hypothesis if the sum of the xi squareds is greater than or equal to K2 or K2 to be determined. I could tell the people that want to run this test that they should not look at this statistic, that they should look at this statistic, in which case I could give them a different cutoff. In other words, I could call this thing K3. It's up to you. It would be an equivalent test. But I'm not going to just call this K3 because I kind of want to stick with this yellow line up here. Like I want to find the K2. Let's finish this off. This whole thing was alpha. And so I've got a chi-squared n curve, and I want to be above something with probability alpha. So we've been calling that chi-squared sub alpha comma 2n or of 2n or something completely different. So the K2 over sigma naught squared is the chi-squared alpha 2n. And so that gives us the K2, and that gives us the test, the best test in all the land. So the best or most powerful test of size alpha of the simple versus simple sigma squared is some sigma naught squared versus sigma squared is some sigma 1 squared for a fixed sigma 1 squared greater than sigma naught squared is to reject the null hypothesis if the sum of the xi squareds is greater than or equal to K2, which we determined to be sigma naught squared times chi-squared alpha 2n. So, right, so this test does not, can you tell I'm in vacation mode? Does not depend on the particular sigma 1 squared that we chose, but it does depend on the relative position because at some point we divided by something and it flipped an inequality. So it does not depend on the particular sigma 1 squared chosen, because at the beginning of the problem, there was no sigma 1 squared. I started out by making a simple versus simple by fixing a sigma 1 squared. But it does depend on sigma 1 squared being greater than or equal to sigma naught squared. So the test is UMP for the simple versus composite. I think I could fit, can't fit it on here. My hand, iPad's not quite big enough, but yay. So used to writing the 2n, our chi-squared distribution was a chi-squared n. Did I even write that anywhere? Oh, well, here, but oops. So I should not have 2n degrees of freedom. In other words, this guy should be n, this guy should be n, this guy should be n. Okay, let's glurt. I'll have to say glurt. Eventually we'll say slurt. which stands for simple likelihood ratio test. So let's GLERT. The GLERT is to the UMP as the MLE is to the MVU. It's more useful. It will exist in cases where the UMP does not exist. So, and, you know, I've been making these problems they've been really pretty much toy problems so that the distributions work out in the end. But the best thing about what we're about to do is some asymptotic results, which will give us the distribution of the lambda kind of thing for large samples. And so we'll be able to tackle many more problems where we can't actually find the distribution or force it into a chi-squared. GLERTs are, I don't know, they're awesome in the sense that they're useful, but they're not most powerful. They're not most anything. So the generalized likelihood ratio test, also affectionately referred to as a GLERT. Okay, so this is where we're really going to be able to handle weird stuff. So our null hypothesis is going to be that theta is in some subset of the parameter space. So that's supposed to be a capital theta naught, versus the alternative that theta is in the parameter space and then like a set minus theta naught. So this capital theta is the parameter space, and then the theta, capital theta naught, is some subset. And then this is everything that's in theta and not in theta naught. Okay, so we're going to define a generalized likelihood ratio, or a GLER. It's not nearly as fun to say. Next time we GLERT, have a good break.